Hello everyone, I'm Dipali Cho, Product Marketing Engineer for TI's high-speed amplifier products. I have with me Preeti Rajendran, who is Product Marketing Engineer for Precision Amplifiers. Together, we're going to be talking about TI's latest op-amps covering OPA835, OPA836, THS452X and 3X, OPAX170, 171, OPAX188, X140 for industrial and consumer markets. Here is the agenda for today's discussion. I'm going to be covering our newest high-speed op-amps OPA835 and OPA836, which are ultra-low power, rail-to-rail output, voltage feedback op-amps, as well as THS452X/3X family of products, which are ultra-low power, rail-to-rail output, fully differential amplifiers. Following this, we're going to talk about OPA836 as a driver amplifier for SAR converter ADS7945. Following this, Preeti is going to talk about precision op-amps covering OPA170 and 171, which are 36 volts, low power, rail-to-rail output, general purpose op-amps. OPAX140, which is precision low noise, rail-to-rail output, fed input op-amp. And then OPAX188, which is 36 volts, zero drift operational amplifiers. Finally, Preeti would walk us through the OPA2188 zero drift topology. I'm going to start over with high-speed products covering low power drivers for precision SARs and the Delta Sigma ADCs, featuring the OPA835, 6, THS452X and 3X family. Let us take a look at our low power rail-to-rail output driver amplifier roadmap. The boxes with white background are the parts that are released to production. The boxes with red background are the ones that we are currently sampling. The ones with the dark gray background are in development, like THS4531, and with the light pink, which is 4541, is a future concept. This roadmap shows both our low power fully differential amplifiers as well as single-ended voltage feedback amplifiers. The OPA835 and the OPA836 are our newest introduction. They are ultra-low power, rail-to-rail output, negative rail input, voltage feedback amps. These amps come in single and dual versions with both standard packaging options to match the existing designs and advanced packaging options for next generation designs. On fully differential side, after a great success with the THS452X low power family of products, we are now working on THS4531, which offers even further low power and higher DC precision than THS452X family of products. Next, let us take a quick look at OPA835 a little bit deeper. The OPA835 is lowest power of the two devices. With only 250 microamps of quiescent current, it is able to deliver 56 megahertz of small signal bandwidth and 160 volts per microseconds of slew rate. It also offers excellent distortion performance in the audio range. As you can see here, HT2 is minus 105 dBc at 100 kilohertz. It operates over the supply range of 2.5 volts to 5.5 volts single supply and plus minus 1.25 volts to plus minus 2.75 volts dual supply. Coupled with power savings mode to reduce the quiescent current down to 0.5 microamps, this device offers a very attractive solution for high frequency amplifiers in battery powered applications. The single devices come also in a RU1 package with integrated on-chip gain setting resistors for smallest form factor in the industry, which is 2x2 mm.
So Dipali, quick question. What about the tolerance for these on-chip resistors?
Hey Preeti, I'm glad you asked this question. Since we are trimming these resistors, The tolerance is 1% for these on-chip resistors, which is pretty good. Thanks for asking this.
Yeah, sure.
So now let's take a look at the OPA836. The OPA836, on the other hand, is the higher performance of the two devices. With typically 1 milliamps of quiescent current, it is able to deliver 206 MHz of small signal bandwidth and 560 volts per microsecond of slew rate. It offers improved noise and distortion performance compared to OPA835. As you can see here, the noise is 4.6 nanovolts per root hertz, and HT2 is minus 120 dBc at 100 kilohertz. Just like the OPA835, it also comes with the RUN package to achieve the smallest possible footprint on PCB. It also has the same tolerance level as we talked about for OPA835, which is about 1%. And besides delivering the excellent AC performance, the OPA836 also offers over 50% better DC precision compared to the closest competing device. As you can see here, the typical drift is 1.1 microvolts per degree C, and input offset voltage max is 1.08 millivolts. This ultra-low power dissipation and higher performance makes the OPA835 and the OPA836 family of products ideal for low power signal conditioning for all kinds of applications where power consumption is a critical parameter, including precision data acquisition systems, battery-operated portable devices, and high-density applications.
So have these products released to market yet?
Very good question, Preeti. Thanks for asking this. So the singles, which is the OPA835 and the OPA836, are already released to production. We released these products back in May 2011. The duals, which is the OPA2835 and the 2836, as well as this RUN package, is currently sampling as well as EVMing. So, and the planned RTM for the duals and the run package is September 2011, so which is about in about a month or so.
Thanks for that.
My pleasure. Now, let's take a quick look at the competitive overview. Consuming 60%, almost 60% lower power compared to the closest competing device, the OPA835 offers 38% lower noise, 32 times better THT, and over 65% better DC precision. So it has a very high competitive edge. You know, this part is really ultra low power for portable applications. On the other hand, we have OPA836, which has over 2.5 times the small signal bandwidth, and coupled with the 10 times the slew rate, this part essentially has over 10 times the 2 volts peak-to-peak bandwidth in essence. It offers 300% lower noise, over 75% better DC precision, and almost 50 times better total harmonic distortion. Combine these specifications, the OPA835 and 836, we offer superior amplifiers with much higher performance to power ratio. In order to expand our offering of the industry's best-in-class performance to power ratio devices for high accuracy data acquisition systems, we made sure that the OPA835 and the OPA836's performance matches very well with TI's, SARs, and the Delta Sigma ADCs. Here, as you can see, we have identified the list of TI's, SARs, and the Delta Sigma ADCs that OPA835 and OPA836 would work well with. For instance, OPA835 is very good at driving the ADS7924 and ADS7950 family of products, which are all 8, 10, 12-bit low power converters. Similarly, one can match the signal to noise ratio and the total harmonic distortion performance when OPA836 is being used to drive the ADS794X family of products.
So Dipali, how do you calculate the minimum bandwidth of an op-amp that is required to drive any of these ADCs?
Preeti, that's a very, very good question. We are going to look at this procedure on how to calculate the minimum bandwidth required to drive a particular ADC a little bit more in detail, where I'm going to walk you through the math that is involved, the calculation that is involved, a little bit more detail in upcoming slides. So the next I would like to talk about our THS452X family. Which is rel-to-rel output, low power, fully differential amplifiers. These amplifiers come in single, dual, and quad versions. We developed this family of products to drive single and multi-channel SARs and the delta sigma ADCs while offering the industry's best-in-class performance to power ratio for high accuracy data acquisition systems. With a slew rate of 490 volts per microsecond, THS4521 can deliver 145 megahertz of bandwidth and yet consumes the quiescent current, which is only 1.414 milliamps per channel, which is half the competition in essence. This part was released to production over a year ago. This ultra low power dissipation and the performance, which is bandwidth and slew rate, makes the THS4521 family ideal for low power precision data acquisition systems and high density applications where power consumption is a key concern. The THS4521 family is ideally suited for applications that require high resolution and precision with superior dynamic range, such as pressure meters, flow meters, seismic equipment, and electrocardiogram machines. In all these applications, you would find that THS452X would be a perfect fit. Ultra-low power dissipation also makes THS4521 ideal for battery-powered devices and other applications with power-sensitive budgets. Now, knowing that there's always an overwhelming need for low-power devices with higher performance, we are now working on THS453X family of products, which is even further lower power, which has even further lower power consumption as compared to THS452X, and is rel-to-rel output fully differential amplifier. This family includes the single, which is THS4531, and the dual, THS4532. They feature accurate output common mode control that allows for DC coupling when driving ADCs. This, coupled with input common mode range below the negative rail and rel-to-rel output, allows for easy interface between single-ended ground reference signal sources and SARs and delta sigma ADCs using only single supply of 2.5 volts to 5 volts. With over 60% lower power compared to the closest competing device, THS4531 can deliver 40 megahertz of bandwidth and 200 volts per microseconds of slew rate. This part is currently in design, starting to sample end of August, and planned RTM is the end of the year 2011. Next, I would like to talk about how we can use the OPA836 to drive TI's newest SAR converter, which in this case is ADS7945. So, what are the key careabouts for op-amp driver selection? For ease, let us look at the datasheet snapshot of ADS7945, which is 14-bit dual channel 2.5 megasamples per second differential micropower SAR converter. So in essence, we need to look at full scale input span. In this case, it was minus Vref to plus Vref. We have to be very cautious about input common mode range. In this case, it was plus Vref over 2 plus minus 0.2, and input also the input capacitance. For optimum SAR ADC performance, the recommended driving circuit is an op-amp in combination with the RC filter. Although this is a common circuit for driving ADCs, it has the potential to create circuit performance limitations, and hence it's very important to choose the right op-amp for a particular ADC which has a a particular resolution in the sampling time and the time and the acquisition time. This is the procedure that shows how to calculate the minimum unity gain bandwidth of an op-amp that can support the particular ADC based on its minimum acquisition time and our rules of thumb for RC filter network and good op-amp stability. So we're going to first calculate the value of K, which in this case is going to be N, which is the resolution of an ADC, whether it's 8, 10, 12, 14, so forth bit. Then we calculate the minimum time constant tau, which takes into account the acquisition time of the ADC over K. Then we calculate the frequency of this added 0, which is 1 over 2 pi tau. And then finally we calculate the unity gain bandwidth by just multiplying that frequency by 4. For ease, now let's take a look at the case of ADS7945, which was a 14-bit converter and has an acquisition time of 80 nanoseconds. We calculate the value of K, comes around 10.4 with N being 14. Then we calculate tau with acquisition time being 80 nanoseconds, comes around 7.7 nanoseconds. Then we calculate frequency 1 over 2 pi tau, which is 20.7 megahertz. And finally, the unity gain bandwidth, the minimum unity gain bandwidth required to drive ADS7945 is 83 megahertz. Now, OPA836 having a bandwidth of 200 megahertz gave us a lot of headroom to be able to drive the ADS7945. Now this is the circuit which shows two OPA836s, two OPA836s configured as differential amplifier driving the ADS7945, each in inverting gain of -1, with RF is equal to RG is equal to 10 kilo ohms. A 2.2 picofarads of capacitor in the feedback helps to minimize the gain peaking and the noise. Gain from the positive input of the OPA836 in this configuration is +2. So biasing to Vref over 4 level shifts the outputs to Vref over 2. With Vref being 4.096 volts and the inputs that swings to plus minus 2.048 volts, that is Vref over 2, the ADC inputs are plus minus 2.048 volts differential and with 2.048 volts common mode. The two 4.99 ohm resistors and this 1 nanofarads of capacitor at the input ADC input provides a single real pole filter to reduce the noise, and more filtering may be required depending on the end application. So this is the block diagram of the test circuit. Test setup that we use, and and as you can see from left to right, we have Agilent 33522A function generator is being used as a signal source. Then we have Allen Avionics 10 kilohertz differential band pass filter, which is used to reduce noise in THD from function generator to get the cleanest possible signal for testing. Of course, then we have our driving amplifier, which is the OPA836, to provide the input buffering and level shifting to ADC as described in the last slide. Of course, we have ADS7945, which is 14-bit dual channel 2.5 megasamples per second SAR converter used to convert the analog input signal into digital output. Finally, we have National Instruments PXI 6542, which provides the data analysis platform used to capture, analyze, and generate the FFTs. Also, we do have the evaluation system, which has the OPA836 mounted with the ADS7945. Since ADS7945 is a dual channel SAR converter, we need two OPA836s driving each input of one channel. So in essence, we need 4 OPA836s to drive the ADS7945. So finally, for measurement comparison, we took two sets of measurements. First, where we had the ADS7945, the OPA836 and 1000 ohms of source impedance. In essence, the ADC was not even being driven because of the source. Excuse me. For the second case, we dropped the source impedance from 1000 ohms to 10 ohms, which is the ideal ADC input driver buffer. Now let us take a look at the measurement results. This slide shows the measurement results of the first case where the ADS7945 was not even being driven because of the 1000 ohms of source. As you can see here, at 10 kilohertz of input frequency for 100 kilohertz of range, the SNR achieved was 52.4 dB. The SFDR was 60.089 dB and the THT was minus 56.8 dB. In essence, the performance was really bad and not at all good. And as you can see here, we are showing the harmonics, the second harmonic, the third harmonic, and so forth. Now, this slide shows the measurement results where ADS7945 was being driven by the OPA836 with 10 ohms of source impedance. In essence, we were driving the ADS7945 start converter. You can see here down below, the SNR achieved was 82.6 dB, SFDR was 103 dB, and the THT was 102 dB. So very good performance, and the harmonics are also so low that they are not even prominent per se. This slide just shows the zoomed out snapshot showing the range all the way up to 1.25 megahertz, and then you can see the numbers here which are the same as the ones that we saw earlier. Finally, in this slide, you can notice when OPA836 is being used to drive the ADS7945, one can match or exceed the datasheet performance. For instance, the spec for THT at 20 kilohertz was minus 92 dB, and with OPA836 being the driver, we can achieve up to 102 dB of THT.
So Dipali, all these results you showed, they're all at 10 kilohertz. So what about higher frequencies like 100 kilohertz?
Very good question, Preeti. Thanks for asking. The OPA836 is able to hold the same performance even at higher frequencies. As we saw earlier in the in the overview slide, the OPA836 delivers the second harmonic, which is the HT2 of minus 120 dBc at 100 kilohertz. So the performance even at higher frequencies is going to be the same. I mean, up to at least 100 kilohertz and even more. I don't expect the performance to be any bad than this. I hope that answers your question. Now,
yeah, thank you.
You're welcome. Thanks. So finally, let's take a quick look at the schedule. Before I hand it over to Preeti, we talked about the OPA835 and the OPA836. The singles are both released back in May. Then we have the duals, which are currently sampling as well as EVMing right now. The RTM for these is September of 2011. Those are all the single-ended amps. On the fully differential side, of course, we had THS 4521, which is released to production back in 2009. And now we have the even further lower power coming up, which is THS 4531. We do have datasheet available. We're going to be starting to sample as well as EVM the end of the August, and the RTM is planned end of the year or January 2012 roughly. So with that, I'm going to hand it over to Preeti to cover the precision section.
Great, thanks Dipali. That was a great overview about the latest high-speed parts from TI. So before I get into a full overview of these devices, I'd like to talk through this roadmap for the high voltage or our industrial precision op-amps. The OPA140 and the OPA209 are the recently released op-amps. They're both low noise, wide bandwidth parts, with the OPA140 having much better precision specs. Then we have the more general purpose op amps, which are the OPA171 and the OPA170. The OPA171 has a single, dual, and quad packages. The packages for the single have all released. I can talk through a snippet of the schedule in the overview of this part. The OPA170 is the lower power version of the 171 with slightly relaxed specs and hence lower price as well. These form a great family of the general purpose high voltage op amps in TI's portfolio. Moving on, we have the OPA188. This is industries as well as TI's first high precision, zero drift, 36 volt op amp. We're currently sampling the dual for this part, and the dual will also release in the next couple of weeks. The OPA07-X, the single, dual, and quad, is the next generation of the OP07, having great precision specs, much lower noise, and can operate in the entire industrial temp range. So now we'll focus on the OPA171 family. This is a great general purpose op amp, also being industry's smallest, offered in the tiny SOT 553 packaging for the single and the VSSOP for the dual. These micro packages reduce the overall board space used by more than 50%. This saves cost instantly than the larger SOC 23 and the MSOP packages. This also has a supply range that goes from 2.7 volts to 36 volts with rotor-rail input and output, a low noise spec at 14 nanovolts per root hertz, and a high CMRR, thus making it an extremely easy part to use regardless of the supply rail system. This also maximizes the input voltage range for use with low voltage sensor outputs. The part also has really low power, the max quiescent current at 475 microamps. This makes it extremely useful even in battery power operations. With DC specs of 1.8 millivolt offset voltage, a 0.3 microvolt per degree Celsius of offset voltage drift, they provide great accuracy and stability over the entire industrial temp range. The part also has EMI and RF5 filtered inputs, and hence this largely improves the noise immunity from wireless interferences. A gain bandwidth of 3 MHz and a slew rate of 1.5 volts per microsecond can make this part really useful with wide signal sources and hence extremely suitable to drive general purpose ADCs. On this slide, I've listed some of the typical applications that we're seeing this part getting used in or even designed into. For example, tracking amplifiers in power modules or as a transducer amplifier, strain gauge systems, precision integrators, many battery-powered instruments. The applications are really diverse, and because of the supply voltage range, the low voltage performance is just as great as the industrial voltage performance. The 171, the 2171, and the 4171 have all released to market. Here under the schedule section, I have listed the parts packages that have released and the upcoming package releases later this year. So to go on, we have the OPA170 family. This is a lower power version of the OPA171. Some of the specs of this part are also a little more relaxed than the OPA171 specs. These are highlighted on this slide. This part will be releasing to market later this quarter. And because of the release specs, also you'll see that there is definitely a price difference between the 170 and the 171 as we target a really wide range of application and different diverse markets. These are the specs that are different from the 171. The lower power at 110 microamps, and slightly relaxed specs in terms of the gain bandwidth and the noise specs. So these are the specifications for the 170 and 171, where we feel that we're really much better with respect to our competition. We have a great offset voltage drift at 0.3 microvolts per Celsius, high CMRR at 104 dB, and a very low input bias current at 8 picoamps max. Now the lower power OPA170 is at 110 microamps max, and the OPA171, which is the lower noise part, is at a 14 nanovolts root hertz typical. These specs have really helped us get customers who are very interested in this part, and again, like I said, over a whole range of applications. So now on to some high precision op-amps. The OPA140 is a recently released high precision op-amp. This has great precision specs with very low noise at 5.1 nanovolts per root hertz and a low offset voltage drift spec at 1 microvolts per degree C max. This also has a very low input bias current at 10 picoamps, and thus allowing for better matching to high impedance sources like sensor outputs. This IB is also 60% lower than our previous generation, the OPA132 from TI's portfolio. Here on the slide, I've actually shown a noise graph or the noise characteristic of the OPA140 and how low we are in terms of our noise. And I have labeled a point which says competitor's device. On the next slide, I listed a total spec comparison, and for comp A, the specs here correspond to the label that I have on the previous slide. So this gives a much better idea where the OPA140 stands in terms of the previous generation, OPA132 from TI, and two of our nearest competitors. The boxes highlighted in green are the specs where we do a lot better than not only our previous generation part, but also our key competition. Now, what I definitely want to highlight is that the specs of the OPA140 are actually much better or are equal to the high-grade specs of our competitors' parts. So under the columns of Comp A and Comp B, there are some specs that actually have a bracket next to them, and these are the specs of the high-grade parts of the competitors. The OPA140 beats even the high-grade specs, and I want to say that we are also just as price aggressive on the OPA140 when it comes to the whole range of the combination of specs that we are providing for that price. The next new part that we're really excited about is the OPA188 series, the single dual and the quad. This is industry's as well as TI's first high precision, zero drift, 36 volt op-amp. The specs that are stellar are the input offset drift at 0.03 microvolts per degree C max, and typical, and a 0.085 microvolts per degree C max. The drift here is 75% lower than our nearest competitor. A very low noise spec at 8.8 nanovolts per root hertz allows for much higher sensitivity for high resolution systems across a wide frequency range. The part is also a very low power part with the 475 microamps max. This makes it an ideal fit for many battery powered applications. So the supply voltage range for this part goes all the way from 4 volts to 36 volts. So not only will this part work great for industrial voltage applications, but it's also a great fit for low voltage applications. Mostly when we see parts like this in the market that are specified from, say, about 5 volts to 30 or 36 volts, they tend not to work or not to live up to their performance when they are operated as a low voltage op-amp. But this part has been tested and will perform just as well, even as a low voltage op-amp. We have some of the typical applications listed there actually on the previous slide, sorry about that, where we're seeing customers who are very interested with this part and who've actually tested it, qualified it, and it's working great. Some of the specifics are electronic weigh scales or as bridge amplifiers, automated test equipment, and medical instrumentation. Because of this wide supply voltage range and with its great precision specs, again, the target market is huge and with a really diverse types of applications. On the next slide, this is a more detailed spec comparison with 3 of our competitors, Comp 1, 2, and 3, as I have listed on those columns. The OPA188 is actually a direct upgrade path from TI's earlier OPA277. It has much higher precision, lower power, and is also priced lower. To specifically highlight, again, I have them in green, where we are doing a lot better than our earlier OPA277 and as well as our competitors. To specifically note that we're achieving a great power to bandwidth ratio. We're low power at 475 microamps, and we're able to still achieve a high bandwidth of 2 megahertz. Our CMRR is at 130 dB. And even with a combination of all these specs, we're still able to price ourselves or be just as price aggressive with the single at 80 cents right now.
So Preeti, how does zero drift make this part so great? Can you shed some light there?
Oh, thanks, Dipali. I was just getting to that. And I'm going to get into why this zero drift is the zero drift topology that has been used in this part is just so great, and why, or how rather, these topologies are implemented. So why should we even use zero drift in the first place? So zero drift topology, however it might be implemented, is going to ultimately help in achieving a very low offset voltage, temperature drift, and excellent long-term offset stability. So over time and over temperature, the stability is great. There's a fast turn-on stabilization of the offset voltage, and a very low flicker noise, or a DC flat-run noise. So there are two ways of implementing the zero drift topology. One is the auto zero topology, and the other one is the chopper topology. So in the auto zero topology, so all op-amps have an inherent error voltage at their inputs. This is also known as the input offset voltage. What I have here is a very, very basic example of the auto zero topology and how it can be implemented. In the picture right on top shows the overall circuitry of this part. There is an internal op-amp. In front of one of the inputs there is a capacitor C1. The other input is grounded. The output of this op-amp is fed back to the input just before the capacitor. There are two switches, T close, that operate at the same time, and T open essentially works the other time. So the first configuration is when the T close switches are closed, as in the center figure. Here, the input offset voltage that sits, or that is marked as VOS on this figure, charges the capacitor C1, and in a sense, all the error voltage gets stored there. In the next configuration, at the lowermost figure, when the T open switch is closed and the T closed switches are open, the offset error that was stored on the capacitor gets added to the input signal. So finally, when the input signal goes through the system, the offset gets cancelled, and you do not see this at the output. The chopper topology is slightly different from the auto zero topology. So the inherent offset voltage of the op-amp that we spoke about, or the input offset voltage, is entirely DC. It has no frequency, or to put it in other words, it is at 0 hertz. So this DC offset voltage signal is fed through a frequency multiplier. And this gives it a frequency that is greater than the chopping frequency that we decide for the system. The high frequency portion of the input signal that comes in to the overall op-amp is fed through the configuration as in the center image. In the center image, we have the T closed switches are closed and the T open switches are open. So this, if you would like to call it, this is the high-speed path for the high-frequency portion of the input signal. For this portion, the DC offset voltage is less significant because the signal is at such high speed, and the frequency of the DC offset is almost insignificant, and the signal remains mostly unaffected when it comes out. For the lower frequency portion of the input signal, this is fed through the configuration as in the lowermost image. In that, the T open switches are closed and the T closed switches are open. Or this is also known as the low speed path, just for convenience. Here, the frequency multiplied offset voltage, which was initially 0 hertz and then fed through the multiplier. So this multiplied offset voltage gets filtered out using a low-pass filter, which has not been shown in this image, because the frequency that was set to this DC offset is higher than the chopping frequency. So using a low-pass filter, we have filtered out the offset voltage, and finally the outputs of both these configurations join, and this forms the net output for the overall amplifier.
So, Preeti, I was wondering, is one of these topologies better than the other one, and why is that?
So yes, actually one of them is better than the other. In fact, I have the comparison on the next slide. The chopper topology actually helps to minimize the aliasing of the input signal, meaning that it has a minimal effect on the input signal that is coming into the overall amplifier. This is very unlike the auto zero topology, since there is the possibility of the topology actually having an effect on the input because of the path that the input signal may be forced to take. In terms of the overall specs, the chopper topology ensures the lowest noise even at very low frequencies and across the entire bandwidth of the amplifier. This is not the case with auto zero topology, which actually shows a higher noise when you compare these two topologies. However, the chopper topology does have a downfall. There is a slightly greater ripple effect that is seen when the chopper topology is implemented versus the auto zero. But all in all, these are both zero drift topologies, and these get implemented because of some of the significant benefits that they have over the standard op-amp topology. As listed here, so it reduces the overall offset of the op-amp. There is a lower offset drift over temperature, and this improves the long-term stability of the part overall. The one major concern that we have with zero drift topologies is the noise. So in the bottom section, I have listed here some of the types of noise that the customers are usually talking about. It's either in the 0.1 to 10 hertz or 0.01 to 10 hertz range, or this is known as the flicker noise or the DC flat band noise. Now this can be corrected with the zero drift topology. I'll get a little bit more into that in the next one or two slides. What is different, if you can go back to the previous slide, what is different is that the glitch or the ripple and the noise across the wide band. This is inherent to the zero drift topology, and the noise across wide band is greater than the standard op-amp topology. The glitch or ripple that is seen with the zero drift is not seen in the standard topology, but because the benefits override some of these concerns depending on the case of the application, zero drift topology is greatly more useful over the standard topology. So in this next slide, excuse me, I have here the typical noise specs for the OPA2188 and the OPA277. We can see that the noise spec for the 2188 remains stable over a very large bandwidth. So compared to a precision bipolar low noise amplifier, the noise density of the 2188 in the 1/f frequency range is really low. And this makes it excellent for use with low frequency applications. For near DC applications also, this allows the designer to be able to filter out this wide band noise with a simple low pass filter, which would be difficult with the OPA277 type of topology. This is the flicker noise that I was talking about, where I said that the zero drift topology would be able to deal with this. The OPA2188 currently is spec'd at having a flicker noise of about 0.3 microvolts peak to peak DC flatband noise. This is actually the lowest compared to any of our competitors right now in the market. So auto zeroed and chopper stabilized amplifiers do have a white noise spectral density, but their noise does not increase without bound, as does a conventional amplifier. So here, if you see, the DC flatband noise kind of stays the same almost through infinity and does not increase This is not the case when you have a standard amplifier, as this DC flatband noise would increase over time and over temperature. As a conclusion, I just wanted to bring up TI's zero drift precision op-amp portfolio. If you go forward, you'll see I highlight that all of TI's zero drift op-amps were in the low voltage space. The OPA188 is actually the first of its kind in the industrial voltage range, and it performs just as well in the low voltage space. Additionally, in TI's zero drift portfolio, the OPA188 is actually at the lowest noise spec of 8.8 nanovolts per root hertz. If you go forward, the circle highlights all the low voltage op-amps. If you hit next again, this is TI's first zero drift industrial voltage range op-amp. So we're really excited about the release of the 2188 in the next 2 weeks. Dipali and I would like to thank you for your time today. We have our contact information up on this slide. Please feel free to send us any questions that you may have regarding high-speed or precision op-amps, and we'd really be glad to help out. We've also listed TI's E2E community support in case you'd directly like to talk to our applications engineers and ask them any questions that you might have about these parts.
Thank you so much.